If not, then we'll just get into the problems right away. So the first person is Davis. If you would please do question number 1. And also I put the problems inside of a slideshow. So if this makes it easier for you to explain your everything with the problem on top. And to edit this or to write on this, you just go onto the top of the Zoom features and you click annotate. And then when you click annotate, you can just draw on this thing.
All right, then. Oh, it's working.
Okay, wait, one second. Let me just, I'm going to transfer my Google to my lower screen so then I can edit it as well. There we go. And I'm just going to turn off my camera now because you'll just see my ceiling anyways. Okay, there we go. All right, Davis. So, okay, so the first step is to list the possible math knowledge that you need for the problem and to show them.
Well, you probably want all of them because you can't really tell the probability because there's 5 red, 6 green, and 7 yellow, and they're all different numbers. So you still have to include them.
Okay. Well,
Right.
do you need as a knowledge, I mean prior knowledge. So do you need any prior knowledge for this problem? For example, if
not
you were
really.
to
No, you
Okay.
don't need any.
Well, okay, let me ask you, how do you find the probability of anything in general?
You get all the possibilities and then you find out which one you want.
But yeah, I guess you could say that's how you intuitively do it, but I want to know how you can find out numerically.
Add all the numbers up except and get the amount of the preferred probability. Then you place the preferred probability in a fraction over the total probabilities.
Okay, so you're saying you want to find the amount of combinations that is not combinations. You want to find the amount of outcomes for your desired outcome, and you want to divide it by the number of total outcomes.
Yeah.
Yeah, anyways, okay, so you can get onto your question.
Okay. Hold on, I think I have to draw for this one. As you can see here, it's a really simple question. All you have to do is add up all the possible outcomes, just combine them, and then put them in as the denominator. Then get the preferred outcome and put it over the as the numerator. Then you already have the answer, and you can then simplify, which would be 4/13. So pretty simple question.
Yeah, exactly. Well, since it's a simple question, I guess we can, expand on this question. So for example, what if I asked you, what is the probability that if we choose 2 of the jelly beans, that both of them would be blue?
Well, if you were to choose 2 jelly beans in a row, well, for the first one, it would be 4 out of 13. So that already narrows our chances quite a bit. So if we were to choose another one, I'm pretty sure, hold on. You would probably want to do 4 over 13 again. And
Okay, if you did 4 over 13 again, would the result be the probability of choosing 2 jelly beans with replacement or without replacement?
well, since you're removing one jelly bean already, so take that out, it would be instead 25. Yes.
Okay, yeah, you're right about the denominator. So if you take away a jelly bean, it would be 25 is the total amount of new jelly beans left. And the top number would be actually 7, because if you take away a blue jelly bean, then
Yeah.
you'll only have 7 blue jelly beans to choose from.
That was my bad.
Yeah, exactly. So the first example you talked about, the 4 over 13 times 4 over 13 is with replacement, which means that basically you take a jelly bean out and it has a 4 over 13 chance to be blue, and you put the jelly bean back, and then when you take the next one out, it also has a 4 over 13 chance to be blue. And then yeah, the second one you talked about is without replacement, where the first jelly bean has a chance of 4 over 13 to be blue, and the second jelly bean has a chance of 7 over 25 to be blue. Okay, now, what if I asked you a question? So what is the chance that you get a blue jelly bean, and then a yellow jelly bean, and then a blue jelly bean in that order? Actually, no, what about this? Okay, so first off, you get a blue jelly bean, and then you get a yellow one, and then you get a green one in that order. So let me just type it out.
So every time take it back or not back?
Oh yeah, okay. And then let's just say without replacement.
So we have to pretend that the other jelly beans are still actually there.
Like without replacement means that if you take a jelly bean out, like you're not going to put it back in.
Okay. Well, the first 2 shouldn't be that bad. It would just be and then it would be yeah. But then when we add the green ones, not only do you have to find the chance, which is just 3 over 13, you also have to find the order, because you have to get it in that specific order.
Wait, just to clarify, without replacement means that you're not putting the jelly beans back, which means that like the first time when you take out.
Yeah, my bad. I just forgot. Hold on. Wait a second.
Six over 24 is 1/4.
Yeah. So
Okay.
now we have all the probabilities, but then when the order, that's when it gets tough.
Well, would you say that like the fraction that you're multiplying together is already in order? Because the first fraction is 4, like for example, if we take a simpler example, let's say that we wanted heads and then tails. So if we wanted heads and then we wanted tails, then we know that heads is 1/2 times
Yeah, that
the
would be a
probability.
25% chance. So
Yeah,
we'd have
exactly.
to have half that.
Would you have to have that though? Because the other possibilities is we can have heads to heads and then tails, and we can have heads to heads, and then we will have tails to tails, and then we will have tails to heads.
Yeah,
So
it
then
would
there's
be a 25% chance of that happening. So you probably would have to cut that in half.
why so?
But then since we have a lot more than 4 options for outcomes, even if we remove 2, then the percentage will be lower.
Oh, okay,
That's
well,
kind of where I'm stuck.
okay, so you think that like if we like for example like
Like
I have a
for
question.
example, it
So
could be blue, yellow, and then it could be red, yellow, or blue instead of green. So it adds even more chance.
Does it though? Because, for example, let's just go back to the heads and tails. Because if we're going to calculate all of the possibilities with the all of the jelly beans, then we'll be here for a while. So for the heads to tails, like heads is 1/2 times tails is 1/2 is 1/4, right? So, but you think the heads and then tails in that specific order has a lower chance than 1/4?
No, it does have 1/4.
Yeah. Yes.
Here. Look, so you have but then yeah, so basically we have 64 outcomes here, yes?
64 outcomes for which one? The jelly beans or the heads
Yeah,
to
the
tails?
jelly beans.
The jelly beans. 64?
I think so. See, here, just this is 4 outcomes, right? So then we do this.
Wait, are you writing something?
Am I?
Because I don't know. Because I'm not seeing like I feel like you're explaining something while writing, but I don't see any writing popping up.
That's strange. Ah, I see. There. Do you see it?
Oh, okay. Yeah.
I have to move it. Hold on.
Okay,
Any
well, for
selection here?
example, okay, well, we can take another example of the different jelly beans. Let's just say for a moment that there was only like one of each jelly bean. So there was one red, one green, one yellow, and one blue. This way it'll make counting easier and we don't have to deal with uneven probabilities. So
Yeah.
you say you want to like see all of the orders that we can have. So yeah, blue, yellow, green, blue, yellow, green, blue, yellow, blue, blue, yellow,
Red.
red, and then there what's the other color? Blue, yellow, yellow.
Yellow.
Yeah, and then basically we can and then we can replace the yellow with a blue here. So we can have like blue, blue, green, blue, 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 and then dot, dot, dot. And we can also have red, blue, red, green, and then we can also have blue, green, green, and then dot, dot, dot.
Yeah, but the thing is, there is, it's not actually 1 out of 64 to get this because there's different amounts of the different colored jelly beans.
Yeah, but we're just taking a simplified version of this problem. So pretend that you didn't see this problem at all. Just pretend that we have like one blue jelly bean, one green jelly bean, one yellow jelly bean, and one red jelly bean. So then continuing on with this, we can see that we have 16 different possibilities here. So 16 possibilities. And then we can do the same thing, but we replace the blue at the start with a yellow, a red, or a green.
We have
So yeah,
64 in total.
Okay, I see what you're getting at. And then, so if we take any one of these possibilities in order, then we get 1 in 64, right?
Yeah, that's what I said. But there's
yeah, exactly.
different numbers of the jelly beans, which is a bit of a problem.
Does this make it clearer?
Yeah. So that means if it's that way, it's 1 over 64.
Mm-hmm. Yeah, so and like if we have a blue, yellow, green, and a blue, yellow, blue, there's literally nothing. Oh wait, no, we can't have, oh yeah, we can't have blue, yellow, blues if, okay, whatever, scrap this example. This is impossible. Okay, let's just redo this example. Blue, red, green, and then we can also have blue, yellow, green, and we can have blue, green, red, and blue, green, yellow. Okay, there. So we have 6 possibilities because I forgot the fact that you can only have one of each color. Okay, so we can have these combinations if we start with a blue, which is 6 possibilities. And then if we start with any other color, it has the same amount of possibilities. So it'll be 24 possibilities, right?
Yeah.
Yeah, so if it has 24 different possibilities, then we see that there's practically no difference between blue, yellow, green, and let's say blue, red, yellow. There's like no difference except that it has different colors. But the colors all have the same quantity, which means they have the same possibility. So each one of them is 1 over 24. And then if we look at the possibility, like the probabilities individually, if we have blue, yellow, green, then we see that the chance of picking a blue on your first try is 1 over 4, because we see the total amount of outcomes is 4, and the amount of blue outcomes is 1. And then we multiply by 1 over 3, since the total number of outcomes after we take away a blue is equal to 3. And then we look at the total amount of outcomes we look at the total amount of outcomes now, which is 2, so it's 1 over 2 to get a green, I guess. So then we have this probability, which is going to be equal to 1 over 24. Okay. Do you agree, Davis?
Hmm. Mm, yeah, multiplying fractions isn't too hard.
Yeah. Okay.
So that means the way that we would solve this problem,
Is that we
oh,
just need to multiply them?
yeah, we just have to multiply them. So going back to this question, hold on.
Yeah, you were right. Yeah,
Yeah.
exactly.
Oh,
Yeah, so it's just like that.
and then we have the answer.
Yeah, exactly. Okay, so does anybody have any questions or comments? If not, let's move on to the second question. Oh, wait, who is this? Wait, why can't I? Oh, wait, I have to use mouse. Oh, wait, the next person to explain is Sean. If you would please explain question number 2.
Okay, I probably did this wrong, but I'll try. So for prior knowledge, you probably want to know like just like probability and stuff, I guess. And that's kind of it. So the process of solving this question is basically you want to know first of all who's not skiing or skating. And we can find that by doing 30 minus 20 minus 9. So we can see that one student is not going skiing or skating. And then the problem says that exactly 5 students went skating and went skiing. So so we can solve this by doing 20 plus 9 to see how many people are like in total are doing one of these 2 activities. And then we can subtract that by 9 to see who's like not doing both of them. And then we can find the answer is 26. I mean, wait, 24, I think. And then you can subtract 24 by the original number, which is 30. So 30 minus 24 is 6. And then therefore 6 should be the answer.
Yeah. Okay. Oh, okay. So I wanted to ask you a question about prior knowledge. So do you know anything about like pi? Like, let me just write it out. So oh,
上一人一起。
okay. So do you know anything about this?
No, I don't think so.
Okay, well, it's a type of food, but it also stands for a principle of inclusion and exclusion. So let's say that, let me just clear up my drawing so it's not that messy. Let's just say that we have a Venn diagram. So if we have a Venn diagram, then we see that we have 20 students here that are going skiing and 20 students that went skating and 9 students that went skiing. And 5 students in the middle, which means that they went both skating and skiing. And we also have the area outside of the Venn diagram, which is the amount of students which neither skate or ski. So then we want to find the number outside of the Venn diagram. And if we want to find the number outside of the Venn diagram, as you said, we want to find the number of both skating or skiing. So if we have skating or skiing, then we want to find the number of these 2 Venn diagrams combined. But we want to be careful. We can't just add 20 and 9, or else we're overcounting. We have a 5 in the middle. So how are we going to deal with a 5? We know that if we look at the Venn diagram, right? And we know that the left circle has 20 people in it. And but in the cross section, there's 5 people here, which means that in the non-cross section of the left circle, there is 15 people. And similarly, we see that there's 9 students that went skiing, but 5 of the students are inside of the cross section. So we know that 5 plus 4 is equal to 9. So outside would be 4. So then we have the total amount of people is equal to 15 plus 5 plus 4. And let's see how we got that. So what we did was basically we did 20 minus 5 is equal to 15, 9 minus 5 is equal to 4, and we added the 5 back. So it's just, as Sean said, 20 plus 9 plus 5. So then this is the principle of inclusion exclusion, is that if you have 2 sets, A and B, let's just say that the 20 students that went skating was A, and the 9 students that went skiing is B. And then inside of the middle, we'll say that it's both A and B. We use the symbol of an upper U to represent and we use a normal U to represent or. Anyways, okay, so we basically have the set of A plus the set of B minus the set of both A and B. Because in A and B, we both counted the set of A and B once, which means that we counted this number twice. So we have to subtract once to get rid of it. Okay, does anybody have any questions on pi?
No.
No? Okay. All right. So, okay, well, what about if we have 3 circles in our Venn diagram? How will we do pi? So if we have 3 circles, 1, 2, 3, how will we do pi? So let's first label the first circle as A, the second circle as B, and the third circle as C. Okay, so first off, let's do A plus B plus C. Which parts have we overcounted? Does anybody know? Okay, so let me say an example. So let's say, look at the very middle. Have we overcounted the very middle? Yes or no?
Yes.
Yes, exactly. So then we have to subtract. But what do we also have to subtract? We have to subtract basically all of the cross sections. So let's first subtract the cross sections that have 2 different areas overlapping. So the cross section with 2 different areas overlapping, let's say we have A and B. So we have to subtract A and B once because inside of A, we had A and B, and inside of B, we had A and B. So we have to subtract one of them to get rid of one of them. And we also have to subtract A and C, and then we have to subtract B and C. Okay, and then after that, let's look at the last cross section. The cross section with both A, B, and C intersecting. So we know that if we have both A, B, and C, then that means we've counted it once inside of A. We've counted it once inside of A, we've counted it once inside of B, and we've counted it once inside of C. So we've counted it 3 times. But we've subtracted both A, B, and C once inside A and B, once in A and C, and once in B and C. So that means we counted both A, B, and C once. So then we have, 0 times, because 3 minus 3 is 0. So then we have to add back one of A and B and C. So we have to plus A and B and C. Okay. Yeah, so basically we're finished now, and this is the pi for an A, B, and C. And then we can do the same thing with A, B, C, and D, and then we'll have A plus B plus C plus D minus A and B and C and so on. But you start to see a pattern here. The terms with only an odd number of things intersecting, which means that for example, A, B, and C they only have one layer, right? We can think of them having layers. So one layer, and then they have a plus sign in front of them. And the ones that have two layers or an even number of layers, so for in this example, we have A and B. It has two layers overlapping. So then we have to subtract it. And then we have to add back A and B and C, which is a part with three layers. Three layers is odd, so we have to add it back. And then if we have four layers, then it will be, we have to subtract the fourth layer away. Okay, that's all I'm going to go on about like Venn diagrams and principle of inclusion and exclusion. Okay, so are there any questions? No? Okay, let's just move on to question number 3 now. Who's next for question number 3? All right, Victor, if you would please present.
Right, so the way I did this question was like super scuffed, but I guess like some prior knowledge you could use for this question is how to factor out like how to factor a binomial, or I don't even know what it's called, but like I guess factoring out like terms and like some from prior knowledge that like whenever you encounter like a question that has like cubes and stuff, like I would draw it out. So yeah. So this question is basically stating that a cube n, which is the dimensions. So n could be as much, so it could be like 4 by 4, like 5 by 5, or anything. So what could be the smallest possible value of n? And n is made out of 1 by 1 by 1 cubes. So for this question, just for simplicity, I used a 3 by 3 cube. So I guess I can draw it, but it's not. I can't really draw it, but basically I did a 3 by 3 cube. So a 3 by 3 cube. So if you look, and it says the faces are covered with gold paint. So, and some cubes have zero paint on them. Some cubes have 1 paint on them, two layers of paint, or 3 faces have paint on them. So basically, the cubes that would have three layers of paint on them would be the side cubes here. And it's also, so the corner pieces, they're gonna have like 3 sides of paint on them. The pieces that are gonna have two faces of paint on them are like the cubes that are like here. And it's only the top and the front facing. And the faces that are only gonna have like 1 face of gold paint on them is just like the 1 face cube in the middle. And the cube that's gonna have like 0 faces of paint on them is the cube in the middle. So we already know that no matter how big the cube is, there's gonna be 8 corner pieces. So there's gonna always be 8 cubes that have 3 faces of them that are covered, no matter how big the cube is. So 3 gold is 8. So now the faces that have 2 cubes. So we know that one side length is. So we know that one side length of a cube is just n. So for example, this side length is n. And then to find the middle area, we could define, okay, so firstly, define the amount of cubes that have two faces of them that are gold. It's basically there's 12 of them on the cube, since there's like 12 side lengths in a cube. And so I made the equation n minus 2 is going to equal one of the side lengths here. So it's going to be, so the amount of cubes that have two gold faces on them are 12 n minus 2. And for the amount of faces that have one piece of gold on them, so this is where it starts to get scuffed. So there's 6 faces of the cube on them. So there's like 6 faces of the cube, right? So there's going to be 6 middle pieces, or just cubes that have one face of gold on them. So if this side was n minus 2, and this side was n minus 2, the amount for the middle cube is just n minus 2 times n minus 2. So I guess so for 1 gold, that would be 6 n minus 2. And for the middle, so if we know that the ones with 0 faces, wait, oops. Yeah, I'll just type that out again. And for the middle, there's just like one piece of, there's just one part of the cube, which is the middle piece for this cube. So for the cube that would have no paint on it, it's going to be since the volume of the cube is like 1 times 1 times 1, it's going to be 0 gold. And we know the side length is n minus 2 times n minus 2 times n minus 2, or just n minus 2 cubed. So yeah, and now that we have this information, I just so we know that the cube that has 0 faces, so one of these things say that the cube of 0 faces is greater than the number of the cube that has 1 face. So it would be the n minus 2 cubed is going to be greater than 6 n minus 2, or we can either write this as a squared, or yeah, I'll just write it as a squared. So now we can just factor out n minus 2 squared from both sides. So it would just be n minus 2 is greater than 6. And now we can just solve for n easily. So n plus 2 and n would have to be greater than 8. So the closest thing to 8 on the answers is 9. So I guess it's C, because it's the smallest possible value of n. So 9.
Yeah, exactly. Also, I have a question. What do you mean by like this solution was scuffed? Because this
Like-
solution was not scuffed.
No, because like I just didn't know if like n minus 2 if I was like doing it correctly. So
Oh, well, you were
yeah.
doing it correctly. And
okay.
I guess that this could be called the, you could say like this is the usual way of doing this problem. Yeah, exactly. So I don't have much to say about this, other than the fact that like this problem, a lot of the prior knowledge for this problem is just that you have to have like intuition. Like there's no really like formulas or theorems that you can remember. It's just like intuition, and it's really easy intuition as well to just like figure out that the cubes with one gold face is 6 and minus 2 squared, and etc. Okay, so that's that for the problem. Thank you, Victor, for presenting. And if we don't have any questions, let's move on to the next problem. Okay, wait. Actually, there's kind of a slight problem with the Google Slides way of doing things. Is that if you're typing text, nobody can see the text unless you like enter it and exit out of the text box. Yeah. So I think who's the next person? Next person is Ronald. So Ronald, for this question, would you like to like share your own screen, or can you use like the pin feature?
I guess I'll use the pen.
Okay.
Okay, for this question, I guess prior knowledge would be, I guess just like basic algebra and maybe the pi method. So the way I did it, I just wrote down the equation, like an equation for finding the number of students that play both sports, but you could do it the pi method. You could, so if you draw 2 circles, one as 25, and the other is 19. And then the middle as the intersection, I just put it as x. You just add them together, right, to get the total number, and then you subtract the total by x because that's the overlap. So you do 25 less 19 minus x, and then that's the total, so that's just equal to 36. So negative x, and then you just solve the equation. Negative x is equal to, subtract 25 from both sides, so you get 11, and then you subtract 19 from both sides, so you get negative 8. And then you just divide by negative 1 on both sides. And then that's the question.
Yeah, exactly. I don't have much to add there, except like when I said pi, like it's kind of like just giving this thing a name. You can just figure this out as Ronald did with intuition. It's just that I guess pi is like a generalized name for these type of situations. Okay, so thank you, Ronald, for presenting. And does anybody have any questions or comments?
No.
No? Okay. Question number 5. Franklin is not here today. I don't think so. Yeah, he's not here.
I can present it because I couldn't finish my question.
Oh, okay. Yeah, sure.
All right. So, also I can't edit the screen right now.
Okay.
So
You can just talk.
we have like 1, 2 in the middle, and it's surrounded by zeros, which is surrounded by 5s, right? And then they're asking how many 2005s we can make. So basically what we're doing is we can just count. So first with 2, 1 0, you can lead up to it with 2 zeros. I'm not sure if you understand that. So basically you can take 2 paths to get to that 0. And then that 0 is connected to 3 5s. So 2 times 5 is 6. And there are six zeros. And 6 times 6 is 36. So it should be A.
Yeah. Wait, okay, so you said that you have a 2, and then it can lead to any of the 6 zeros, right?
Yeah.
Yeah, it can lead to any of this 6 zeros, and you said that you had 6 possibilities to do 0, 5, right?
No, because we have to make what, so basically if we take 1 0,
Yes.
right? There are two zeros connecting to every 0.
And
Right?
there's 3 5s connecting to every 0.
Yeah.
Yeah, exactly. Yeah,
Yeah.
okay. Yeah, that's right.
Yeah.
Okay. And I don't think there's too much to say about this problem. Like, we already covered a lot of what was to say like earlier, and you can just figure out this pretty easily. So thank you for presenting. And does anybody have any questions? No? Okay.
No.
All right. Let's see. Question number 7. Number 6. Who's doing number 6? Okay, Jijan. Jijan, if like, did you wait? Okay, yeah, whatever. Okay, oops. Okay,
Okay.
Jijan, would you like to present? Yes.
Okay. Yeah. So we know that these prices are all equally likely. So for the first one, so we want to make 50. And so first we can see the total amount of possibilities. And so there's 3 possibilities for Ben and 2 possibilities for Jamie. So we just multiply 2 and 3 and we get 6. But we want to get 50. And so we see how many possibilities there are where we can add to the sum of their 2 prices will equal $50. So first we have the possibility that Ben gets 20 and Jamie gets 40. And so each of these are 1 out of 3 and 1 out of 2 respectively. So that's 1 out of 6. So that's one possibility that has a probability of 1 out of 6. And another possibility is 10 and 40. And that we do the same operation and we get 1 out of 6. And so we add these 2 values together, 1 out of 6 plus 1 out of 6, we get 2 out of 6, and we simplify that into 1 out of 3.
Yeah, exactly. And I guess you could say that this question is also kind of like basic probability. Let's see. So wait, what can I expand on this question? I feel like not really too much. Yeah, whatever. Okay, so thank you for presenting, Ji-John, and let's just go on to question number 7. Question number 7. I'm assuming you guys don't want to present this one, so I'll just present it. Okay, the average value of a minus b squared plus b minus c squared plus c minus d squared plus d minus e squared plus e minus f squared plus f minus g squared over all possible arrangements a, b, c, d, e, f, g of the 7 numbers 1, 2, 3, 11, 12, 13, 14 is how much? Okay, so first off, for our possible math knowledge, we need to know, as we can see that there's squares in here, so we might possibly need to know how to expand squares. And we also need to know how to find the average, which is a spoiler, but this is a key point of the problem, finding the average. Okay, Anyways, so then let's go on to the strategy to solve this type of problem. What will be the strategy to solve this type of problem? So if we see an equation with brackets, we sometimes want to simplify it. And simplify as in we want to expand the terms and see if some terms cancel out. And if we want to find the average of a set of numbers, then we have to add up all of the values, like all of the values, and then divide by the amount of values there are. Okay, so first off, let's expand. And I'm pretty sure if I'm sharing the screen, you guys can see my text box, right? Yes, okay.
Yeah.
Oh, okay. So the first term, I'm not going to write it down. So it's a minus b squared, a minus b squared. If we expand, like this is kind of prior knowledge, but if we expand a term x minus y and we square it, what will it equal? Okay, let's do this step by step. So x minus y squared is just x minus y times x minus y. X minus y times x minus y. And then if we, let's first expand the first bracket. So then from the distributive property, we have x times x minus y times x minus y. So it's equal to that. And if we continue to break down the brackets, then we get x squared minus xy plus, because why is it plus? Because if we have a negative times a negative, it's a plus. Plus y squared, and then minus xy. And this is equal to x squared plus y squared minus 2xy. Okay, so now we have expanded x minus y squared. And we can do the same thing with just the a minus b, b minus c, etc. And we get in the end, we have a squared, I'm just gonna write it like this, plus 2b squared plus 2c squared plus 2d squared plus 2e squared plus 2f squared plus 2g squared. And then, so we have like all of the square values because we know that a minus b squared has an a squared plus a b squared. B minus c squared has a b squared plus a c squared, and etc. Oh wait, no, this is just g squared. Okay, so after that, we still have to add on the minus 2xy's. So the minus 2xy's, we have minus 2ab minus 2bc minus 2cd minus 2de minus 2ef minus 2fg. Okay, so now that we have these values, then let's see if we can find the sum of, like, if we can find the total sum and divide it by the number of values. And what does that mean? That means that we have to iterate through all, we have to find the sum of like this value over all of the possible arrangements, A, B, C, D, E, F, G, of the 7 numbers 1, 2, 3, 11, 12, 13, and 14. So basically, we have to like, so we can set A is equal to 1, B is equal to 2, C is equal to 3, D is equal to 11, E is 12, and etc. And then we also have to add on A is equal to 1, B is equal to 2, no, B is equal to 2, and C is 3, 11, 12, 14, and then 13. So that's a different arrangement. And we have to go through all of these different arrangements and add them together. And then we have to divide by the total amount of different arrangements we had. Okay, so first off, let's take a value, like let's take a squared. So if we take the value a squared and we look at all of the possible like numbers it can iterate from, we know that a squared can iterate through 1, 2, 3, 11, 12, 13, or 14. And now the question is, how many of each do we have? So how many times do we have a squared? No, a is equal to 1. Well, the amount of times that we have a is equal to 1 is the amount of like permutations of b, c, d, e, f, g, which means that like, how can we assign the values from 2, 3, 11, 12, 13, 14 differently to b, c, d, e, f, g? And Then we ask the next question. How many times do we have a is equal to 2, and etc. But we find out in the end that these two values are the same. And why do we know that? We don't need to do any calculations to get that these two values are equal. And why is that so? Because we see that, so for the how many times do we have a is equal to 1, we have to find all permutations of 5 numbers, which are different. So 5 distinct numbers. And permutation just means different ways you can assign the numbers to the variables. And then if we look at the amount of times we have for a is equal to 2, then we have the permutations of, again, 5 distinct numbers. And we have the same thing with a is equal to 3, 11, 12, 13, and 14. So that means the amount of times that a is equal to either of all of these numbers is equal, which means that we can just simplify it as one time. We can simplify this as 1 time. And we can simplify this as 1 time because we're looking for the average. And in the end, the average will still be the same. So then if we want to find the average of a squared itself, then the average will be 1 squared plus 2 squared plus 3 squared plus 11 squared plus 12 squared plus 13 squared plus 14 squared divided by 7. Okay, so now we know how to find the square numbers because we can do the same thing with b squared and c squared, but we have to multiply a 2 in the end. Now, what about 2ab? How are we supposed to find 2ab? Now, that's a tricky question. We have to go through all of the values for a and then all of the values for b and take the average. Which means that we'll have to take 7 times 6 is equal to 42. So we'll have to take somewhere around that. And we're not going to, and we know that if we find AB, then we can likely find BC and so on. But to find AB, it's kind of time consuming because we have to go through too many values since we have the 2 variables here. Or at least it's not going to be easy because we'll also have to be dealing with a lot of large numbers. Okay, well, let's go back a step. What if we didn't expand the values? Because we see that when we expanded the values, it didn't seem to get easier. Like we have this very long equation, longer than the original one, and we didn't get rid of any values at all. So what if we just didn't expand this equation at all? Now, we can take the same principle of finding the average and apply it here as well. So we have a minus b squared. So if we want to find the average of all a minus b squared, average of all a minus b squared, what do we do? So we do the same thing as before. Okay, so let's assign a. We know that we can have, let's say that we have pairs AB. Pairs AB. And then we look at all of the different values for AB. So then we can have 1, 2, 1, 3, 1, 11, 1. Okay, and then if we have a is equal to 2, we have 2, 1, 2, 3, 2, 11, ... And then we can also start with 3. So let's just type ... to save time. And we can also start with a is equal to 14 and b is 1, 14, 2, ... all the way to 14, 13. So we have a lot of these values, but we note it, and we have to take the sum of them and then divide by the amount of these values. But we notice that half of these values is equal to the other half. What do I mean? Well, as you can see, for example, if we have 1, 2, and 2, 1, we know that these are the values for a and b. But if we do a minus b, so 1 minus 2 squared, it's going to be negative 1 squared, which is equal to 1. And if we have 2, 1, then we know that 2 minus 1 squared is equal to 1 as well. So these two values are exactly the same. And then we can also find a value which is exactly the same as the pair of 1, 3. And that value would be the pair 3, 1. And this is because it's basically A and B swapped around. But if it's swapped around, it just means that A minus B will have its sign change. But if A minus B has its sign change, it gets squared. But a sign change squared is always equal to positive. So therefore, they are the same. Which means that we can just eliminate half of the possibilities. Okay, so if we eliminate all of the half of the possibilities, let's just take all possibilities for A minus B, which are positive. So then we have 2, 1, 3, 2. Actually, I should write like 2 minus 1, 3 minus 2. This way we can skip a step. 11 minus 3, 12 minus 11, 13 minus 12, and then 14 minus 13. And then we have okay, so this is all of the different, not necessarily different, but we have here all of the different pairs of AB, which doesn't come out as AB rearranged. Okay, so now that we have all of these values, then let's just find the squares of them and let's add them up together. So our squares, we see that in our first row, we have 2 minus 1, 3 minus 2, 12 minus 11, 13 minus 12, and 14 minus 13, which are all 1. So when they're squared, they're still 1. So we have 1, 1. 11 minus 3 is 8, so it's 64. 1, 1, 1. And then the next one, 3 minus 2, this is 2. And then the next one is 9, so 81. Oh, wait, no, 4. My bad. And then after that, we have 81 again, and 4, and then 4. And then we have 100, 100, 100, and 9. Wait, 1, 2, 1, 1, 2, 1, and 1, 2, 1. Yes. Okay, and then we have 1, 4, 4, 1, 4, 4, and then 1, 6, 9. Okay, so if we sum all of these numbers up, to save you more time, I will just tell you the answer. It's 1372. Okay, so now we've summed all of these numbers up. Now we need to count the amount of numbers there are here. And the amount of numbers there are is going to be equal to 21. So then we get this number. This is the average. This is the average of all A minus B squares, which means that it also applies to B minus C squared and then C minus A squared, because these values are essentially symmetrical, other than the fact that they have different variable names. So that means that if we want the total average, then we just add the average of the terms up. So if we add the average of the terms up, we have 1372 over 21, and then multiplied by 6. And we see that the 6 and the 21 can reduce. So we have a 2 here and a 7 here. And if we do 1372 divided by 7, we get 196 times 2. And the value to that is going to be equal to 392. So the answer to this question is D, 392. Okay, so does anybody have any questions on this problem?
Yeah, why did you divide the 21 by 3?
Oh, why did I divide 21 by 3? Because
Yeah.
oh yeah, I should write my process more clearly. So this times 6. And the reason we do a multiply 6 is because
Oh, yeah.
there's 6
Yeah.
values here. Yeah. Yeah,
That
good
would-
question. though.
Dude.
Good question. Okay, there we go. That's clearer. Any other questions or comments?
Wait, other than like dividing 21 by 3, like not really.
Oh, oops. Okay, yeah. All right. So now let's go on to our summary. So the key points, the trick, and the experience, and our conclusion. So the thing is that when at least I did, when I first tried to solve this problem, I first tried to go expanding, because sometimes it's good to expand things out and to see like different relations and to see like to get rid of some variables. But in this case, expanding didn't work. So then we backtracked. And then as always, to find the average of like I guess of anything, you just want to find all the sum of the total, like the sum of like just the entire sum divided by the number of different values. And this, I guess this problem is kind of straightforward. I'm pretty sure you can still solve it relatively quickly if you expanded and then looked. If you expanded and looked for the average of any 2AB. Excuse me. So yeah, all right, that's that problem. And are there any others ways for a solution to this problem? Personally, I don't really know. I guess you could say another way to this solution is if we expanded and found the average that way. But I personally think that this way without expanding is better. Okay, so does anybody have any comments or questions? If not, let's move on to the last question, question number 8. Okay, question number 8. So, does anybody know how to solve this problem?
I know.
You know? All right, go ahead.
Okay, so triples of positive integers A, B, C. So basically just means 3 sets of positive integers. They have to be 6AB equals C squared. And then C has to be lesser or equal to 35. And B has to be lesser than C, and A has to be lesser than B, right? So basically you can just go from 35 down to 1 and square every single number and then divide them by 6 to find if they are possible, and then find the result of that and try and use AB to basically fill in to get that number, if that makes sense.
Okay, yeah, I see. That makes sense. So we have AB is equal to C squared divided by 6. So, okay, so we know that we know that C squared has to be divisible by 6. Now, we also know that C is less than or equal to 35. So can we deduce any information on what numbers C can be?
C can be 30, 24, 18, 12, or 6, I think.
Yeah, exactly. So these are the values of C. And so are you suggesting that we go through all of the values of C and we see which values of AB work?
Yeah, you just square 30 and divide by 6, and then so on and so on, and then you get 150, 96, 54, 24, and 6.
150, 24 divided by 6 is equal to 4, so that's 96. Yep. And then 18,
before
18, 3, so yeah, 72. And then 24, and then 6. I think so. Yeah.
and then basically you just like see AB have to be smaller than 30, and they when they multiplied they have to equal 150, so you can get I think 15, 10, and 625. And then you do this and then you just go through all of them.
Yeah. Okay, so we have 10 and 15 and 6 and 25. If we check, wait, let me just see. Yeah, that's all of the values. And then if we go down, so we have AB is equal to 96.
And we have like a 12, 6, 16. And those are all the values.
Yeah. And then if we have AB is equal to 54, I think. Yeah.
If it's 54, then we get 9, 6, I think.
Yeah.
Yeah.
Then AB is equal to 24.
4, 6, and 3, 8.
And then AB is equal to 12.
And
Oh wait, not 12. My bad.
Yeah.
6.
yeah, you get 3 and 2.
Okay. And yeah, exactly. These are all of the possibilities. So can you tell us how many possibilities these are?
If we count that, it should be 9.
1, 2,
Oh, 8. 3,
yeah,
1,
8.
yeah, 8.
So 8 different AB which work. Therefore, we have 8 different ABC. Yeah, exactly. Okay, all right, so let's talk about some of the other steps of this question. So do you have any idea of the possible math knowledge we used? Like what math knowledge do we have to use there?
Do you simplify, I guess?
Yeah, so factoring. So we needed to know factoring. So let me just write, actually I'll write it over here. Wait, can I click tab? Yes, I can. Okay, so math knowledge. So we needed factoring, aka simplifying. Anything else?
No, you kind of just have to.
You just
Uh,
bash it.
Yeah.
Yeah.
You need to know what to count as well to do this question.
Yeah, exactly. Okay, well, for these questions, it doesn't matter what their name is, but they're just called Diophantine equations, which means that they have they don't have a unique solution, but the thing that is limiting them is the fact that they are positive integers. So for example, if we didn't have the positive integers thing here, then that means we can basically have infinite values for ABC. So that's a one limiting factor, and you have to know how to work with you have to use different ways to solve for the Diophantine equation. In this case, it was pretty easy because we already were given a factor, but sometimes when you have a Diophantine equation, there's addition and there's subtraction, which makes it harder because if you want to look at positive integers, you want to make it into a number multiplying another number. So let's say, actually, I'll take an example. So no, I'll talk about an example after this. So yeah, that's basically the math knowledge, just factoring or simplifying. And then can we talk about the strategy to solve this problem? actually, you guys already said the strategy. The strategy was basically just try all of the values. So we had to try all of the values to figure out the answer in the end. Or we can also call this casework, because we can't just go from like C is equal, like we have to like break down the different cases so that we're not stuck for an entire day counting. Okay, and then let's go on to the summary. So key points, trick, experience, or conclusion. Do you guys have anything like different from the strategy and the knowledge? No? Okay. Yeah, that's what I thought. And then is there another way to the solution? Is there another way to the solution? Do you think so?
I mean, there probably is going to be one out there, but I'm pretty sure that this is the easiest.
Yeah, I know another way to solve this solution.
I
You
knew it.
just I know. You just try all of the numbers from A, B, and C that are usable. So basically, as you can see, there's something called a computer program, which means that if you try all of the values of A, B, and C, all of the values of A, B, and C, then we can try all of those values in at least since we know A has 30 like at most 35 possibilities, B has at most 35 possibilities, C has at most 35 possibilities. It's 35 to the power of 3, and this isn't a really large number for the computer to try. So it can just figure this out in like 1 second. But obviously we're not using a computer program during a contest. But it is another solution though.
Did you
Okay.
take the rules?
Well, I'm pretty sure the rule says that you're allowed a calculator, but it can't have like intelligent function. So I guess like a computer is technically a calculator with intelligent function. Anyways, okay, so yeah, so I wanted to get back to the point about like equations where you have to solve for positive integers and that you want to try and factor, because this problem, like, it's already in factors, so it wasn't that hard to figure out. But let's say if we have another problem with xy, right? If we have xy plus x is equal to what should we do? Negative y plus 31, and then we have to find out all xy. And if we wanted to figure out this equation, let's just we move all of the x and y variables onto one side and we try and factor it, or we can move it onto the other side. But yeah, and this actually factors into x plus 1 times y plus 1 minus 1, because 1 plus 1 is 1 times 1 is 1 minus 1, we get rid of the 1, and it's equal to 31. And if we move the 1 to the other side, it's equal to 32. Now this is really easy to figure out, and the reason for that is because we've broken the variables into factors, which means that we can take all of the factors of 32 and do basically what we did in this problem up here. So like we know that obviously 32 can be broken up to 132, to 16, and etc. And we can plug in these values and figure out the values of x and y. So that's an example of you're trying to find all of the sets of positive integers that satisfy a condition. Okay, so yeah, I'll stop rambling on. So does anybody have any questions or comments?
Nope.
No.
Nope. Okay. All right. So one last thing before 等一下，还有多少时间呀？
那没关系，你可以继续。
继续啊。
如果你想讲。
Okay. Yeah. I'll just talk about one more thing. So hopefully I don't take too long. Okay, let me share this whiteboard. Screen sharing is paused. Resume share. There we go. Okay, let's say if we want to select. Okay, so let's say I have 10 different, no, actually we'll make a smaller amount. Let's say I have 3 different t-shirts to select from. And I want to select 2 of them for some random reason. So how many different ways can I select the t-shirts? Okay, what do you guys think for this problem?
6.
6? Why so?
So basically we have so we can have X, Y, and Z, right? So we can either brute force it with X, Y, X, Z, Y, Z. Hold on. Yeah. X, Y, X, Z, and Y, Z. So that should be only 3. Yeah.
Yeah. And you got 6 because I'm pretty sure you did like 3 times 2 is equal to 6.
Yeah.
Because there's 3 possibilities for the first one and 2 possibilities for the second one.
Yeah.
So the first one we have is we don't care about the order. We don't care about the order, which means that, like, for example, it doesn't matter if I pick the red t-shirt first or if I pick the blue t-shirt first, like, or I guess the X t-shirt and the Y t-shirt first. And the second one, we do care about order. So there's 3 ways to pick the first t-shirt and there's 2 ways to pick the second t-shirt. Now let me generalize this. What if we have usually it's n. If I have n different t-shirts and I want to select m of them, how many different ways can I select the t-shirts? Well, now I'm not gonna ask you guys this. If you know, you know, but we have something called, actually, I should just write it out. No, actually, whatever, I don't care. Okay, so usually it's like kind of like a fraction with brackets around it, but without the line. I'll show you guys later. But so we have C in M, which means the different combinations of selecting M different things from in different things and disregarding order. So first off, let's see. So if I wanted to select the first t-shirt, then I would have in different ways of doing so. If I wanted to select the second one, I would have in -1. In -1, and then I multiply by in -2, and then ... until I run out of t-shirts. So I multiply this until I have no more t-shirts to choose, which is n minus m minus 1. Because this would be the mth t-shirt that I'm choosing, and after the mth, I'm not choosing the m plus 1. Okay, so what is this equal to? Can we write this out more generally? We see that if we did n times n minus 1 times n minus 2 all the way to 1, it would be n factorial. But then if we divided it by m factorial, then we would have this result here, because we're getting rid of the latter part, which is n minus m. Wait, this should be plus 1. N minus 1, n minus m, and then n minus m minus 1, and then ... But we're getting rid of this. So if we want to get rid of this, we have to divide. And what do we divide by? Well, we see. Wait, no. No, that's not how you do it. This should be n minus m. Yeah. Okay, there we go. Okay, so then if we want to divide it, then we have to divide by n minus m factorial, and we get this result. Okay, but this was if we regarded order, which means that just like in the previous example, when Jason did 3 times 2, we had the n is equal to 3, and then we multiplied by 2, and we divided by a 1. So we got rid of a 1. But if we wanted to disregard order, on the denominator, we have to multiply by another n minus m. So we multiply by another n minus m factorial. And why do we do this? Because we see that there are n minus m ways to arrange these or arrange m items. Why are there? Oh wait, whatever. No, that's not how it works. Oh. Oh. No, it should be m. It should be m factorial because we have m different ways to rearrange these m different items. Because if you think about it, if instead of m in different t-shirts, I have m different t-shirts, and I wanted to select m of them, which means that I would just be arranging the m t-shirts in different ways. Okay, so I have m different ways to arrange these t-shirts. And so basically what I would be doing is that I would be doing, like, how do I explain this? Like, actually, whatever, I'm not gonna explain this. So I just wanted you guys to know that there is a thing that is like, oh. So in n, pick m. And then this is going to be equal to n times n minus 1, and then dot dot dot, all the way to n minus m plus 1, divided by m factorial. Yeah, okay. So this is just basically like for future reference, if you wanted to select m different t-shirts from n t-shirts, and you wanted to disregard order, which means that it doesn't matter what order it is. And this would be the equation to do so. And I'm just going to stop rambling there. And if there are no questions or comments, then that will be the end of class.